fault. But yeah, I am Dave Bjorkstrand. I'll introduce myself properly on slide 2. But you're here to listen to me talk about UK buildings and carbon emissions. How big is the problem and how we solve it? I gave this title to Ellie just before writing the presentation, actually, and the more I wrote, the further I went off piste from the original title. So hopefully you'll forgive me for my lateness and also for making a minor change, which is probably actually fairly major. So we're not going to do that. We're going to do what does a building service engineer do and why is it so important? So that's completely my fault because the original title was come up by me. But the main fault in the original title is the use of the word we. We assumes that everyone listening finishes university and ends up working within the building sector, focusing on energy and carbon emissions, which is a fairly big assumption for me to make, bearing in mind it's likely that few of you actually have heard of the term building service engineering or have any knowledge of what we actually do. So for those of you who are particularly taken by the title though, don't worry, I will be talking about carbon and buildings and happy to take as many questions after, and then I'm totally happy for you guys to jump in and just shout any questions as I roll. So another reason for the slight change in emphasis, I suppose, is that with COP, with the Engineers Declare movement, with the media focus being a bit more energy and carbon focused, it's kind of a bit easier to find out about how important building emissions are and carbon emissions in general. But what is harder for you guys to find out is what being a building service engineer is like, and to get an appreciation of what you might be doing as a building service engineer and what problems you may be solving. Because yeah, that's what I enjoy doing, solving problems. Okay, so like I said, that's me in the middle there, with Ellie with us as well. So yeah, that's the whole of E3 Consulting Engineers. That was our summer sort of social where we went foraging. It was great. And then for me, in terms of my academic and professional life, I did chemistry, biology and maths at A-level a long time ago in Tunbridge Wells, down in Kent. I took a year off traveling after doing that, so like a gap year. And then I went to Cardiff University for 4 years and graduated with a master's in civil engineering. I then took another year off traveling and started my proper job. I'd had lots of construction and hospitality sort of stuff in between uni, but then yeah, my proper career job, I suppose you could call it, at a small sustainability consultancy called Ecospheric up in Manchester. And then from there, I moved to a medium-sized building services consultancy called Max Fordham, where I worked for 6 years. They were great. And then I took another year off traveling. And after that one, I moved to Bristol and started working at E3. And that was about 2.5 years ago. Along the way, I submitted my documents and achieved chartered status about 5 years into my career. That's so I'm a chartered building service engineer, CIBSE. So that's that fairly low definition image just there. And I also studied for and passed my Passivhaus exam last December. So I'm a qualifier certified Passivhaus designer. And again, any questions about those two, probably best to wait for the end, but I'm happy to talk about the process and what's involved in learning and getting those two certifications. I suppose a bit further, I'm like a lot of engineers, mildly dyslexic, so my reading won't be super smooth. I'm left-handed, which is another thing that's common in engineers. I have terrible handwriting and I am awful at drawing. So yeah, if you, I'm sure a few of you share some of those characteristics, and if you don't, good for you. So what does a building service engineer do, or or what are they? What do they even look like? So it's an umbrella term. So I'm a building service engineer, but more specifically, sort of under that umbrella, I'm a mechanical engineer, and I work in a design consultancy with other mechanical engineers and some electrical engineers too. There are lots of other jobs that you can be doing which fall under the building service engineer umbrella. You could be a lighting designer, you could be a ventilation grill designer, you could be an access control specialist or a sprinkler specialist, or you could be a PV, so photovoltaics or solar panel designer, or you could be a contractor. You could be like a mechanical or electrical contractor, which means you're a bit more of a builder rather than a designer, a doer rather than a thinker maybe. And yeah, these images show you a few of the things that you might be doing in a job in building services. So this guy here is playing around with probably a MCP, so that's like a motor control panel, and it will be controlling some stuff. It might be mechanical equipment, it might be data equipment, could be anything. And then down here, Ellie's been doing a bit of this while working for us, so kind of lighting design, so picking light fittings and then playing around with their outputs and their positioning to give the right outcome. So this obviously is stage lighting for a band performing. But that could be office lighting to make sure that you've got enough uniformity and light levels for your desks and your office workers. This here is some CFD analysis, so some real sort of tech modeling. So what you've got there, that might be a facade designer that wants to make sure that enough air is moving through or in and out of the building. And the same sort of process is used for kind of analyzing kind of smoke through buildings too. So that's really important these days. And then, like I say, you this lady here is fitting a kind of heating system. So that might be a world of building services that you may find yourself in the future. So here's a smart art I made, which probably me doing smart art to you guys is like the equivalent of my parents maybe doing like word art in an email. So forgive it if it is that basic. But it kind of shows where we sit and how a building gets designed. In the middle, you've got a client who wants to build a building, and then a design team that gets appointed to do just that. So the core of the design team generally is always us, an architect and a structural engineer. And then we might get some other people to join us, like, so that's the others category. So you might have like landscape architects, facade designers, fire specialists, sustainability consultants, that sort of stuff. Our clients vary, but generally it could be a university, it could be a school trust, a housing association, a private individual who wants to build their own house, or a company. So it might be a company that want to build some offices, or I don't know, a warehouse or a manufacturing facility, or anything that you can think that a building does or houses. So that's around 80% of the work that I do. And then I probably have about 20% that's slightly more energy focused. So that might be, currently we're getting a lot of job inquiries from people with large properties or estates who want to move away from fossil fuel heating systems to low carbon systems. So that's a pretty rewarding part of the work that I do currently. So next, let's have a look at some of the outcomes or buildings, I suppose, that I've been involved with in my career so far. So yeah, the following examples aren't necessarily the best projects or the most important ones, but they are the ones with the best photos. So that is the criteria for the next few slides. The project on the right is St Swithin's School in Winchester. It's a good photo. It shows some really nice architecture by a company called Waterson Cohen, this photo kind of shows some of the outcomes of the environmental analysis that we did during the design, how it finds its way into the building. So just here, these lights here are kind of roof lights, and they push natural light down into the ground floor. So it means that you get natural light deeper into the floor plan, and that means that you need to use less artificial light. So it saves a bit of money, and also it's nicer for the kids to have a bit more of a interaction between the day, how the day goes on, and have a bit more of an interaction with the external environment. We've also got these PV panels, so solar panels. They are probably designed to do about 50% of the load per year. So we did a lot of energy modeling to find out what we thought the school might use in a year, and then we sized a PV array to then kind of match half of that energy demand. We also left a lot of space on this building here for PVs in the future. And hopefully that will be used in the future for more PVs, and maybe they can realize some sort of net zero carbon, or reduce their annual electricity usage. And then also we've got the more nuts and bolts stuff. So this here is a ventilation system. So there's supply air that will go through this duct here into the rooms and then extract from here. And then the heat from the extract will be recovered. So that's like a mechanical ventilation with heat recovery system. And then these ones here, these smaller ones, are just toilet extract fans. Okay, that's quite enough on that. The picture on the left is a plant room. So yeah, probably if someone showed me that in my university career, I would not know what was going on. And kind of between us, like I'm not entirely sure everything that's going on in there, but a building service engineer who does a lot of detailed mechanical design certainly would. So yeah, they'd know all the things there is to size all of these things, and yeah, be able to use the tools to analyze the loads to make sure that those are the right components working in the right way. But yeah, this plant room has big pipes and big pumps and kind of big everything, and probably has a big energy output, whether that's heating, cooling, whatever. The school building on the right, that is not the plant room from the school. The school on the right has big walls and big insulation and high performance windows and good air tightness and heat recovery ventilation. So it actually runs on its heating comes from a boiler that's probably very, very similar to the boiler that you guys might have in your student houses. All right, let's carry on, please. So this, oh, I've stalled. Ellie, what's happening? Can you see the, oh, right.
Oh, runs.
Yeah, hold on, I'll go back a few. Can you hear me okay as well?
Yeah, there's no lag at all.
Lovely. Oh, it's really rocketing through now. Oh no. Okay. Is that on a very brutalist Stark building by 6A Architects?
Yeah.
Okay, cool. Good. So this is another project that kind of highlights a different role, a role where we are kind of secondary to the architecture. As you can see, the architectural vision and brief for this building is very strong, and it means that we need to kind of work in the background to make sure that that it's heated and cooled, and our equipment doesn't detract from the aesthetic. Okay, good. All right, and this is another one. I'm going to kind of talk about this one for a while because it's got some really interesting roles that we undertook for the project. And it gives you quite a nice overview of some of the more interesting things that we would do as part of a design team for a building. So this is St John's College for Oxford University. Again, very strong architectural vision with all sorts of constraints. So as you can see on the right, it's linked to a grade 1, so the highest kind of like heritage listing you could get for a building, called the Canterbury Quad. And it also has the Great Lawn in front of it. So you can see in the foreground, that lawn is the lawn for the president of the college. And because it's for the president, we aren't allowed to have any windows overlooking the lawn so that the president can sort of wander around and have his thoughts to himself. So yeah, it was quite a big project. It costs a lot of millions to build. And it's worth mentioning because, like I say, the roles that we did. So one of those was the modelling. We did lots of modelling for this building. The brief was to provide a net zero carbon building. So that means whatever carbon emissions were used to provide heating, hot water, lighting, and electricity to the building, we needed to make sure we sized a solar panel, so PV array, big enough to offset all those emissions. So that means modeling the energy. So that was using some kind of simple spreadsheet analysis, but also kind of an hour by hour weather file that was then applied to the building structure and the building fabric performance to work out how much heating and cooling would be needed per year. We then did some modelling of ventilation in the library space using CFD. There's quite a lot of low and high level openings within this building. So we wanted to make sure that we weren't over ventilating the space, but we were also providing enough fresh air to keep it fresh, to keep the humidity down, and also keep the stop any buildup of odours or CO2. And so that was done through CFD. We also, I mean, this was kind of not a standard thing a building service engineer would do, but just beneath here is like a pond. And we did some analysis on how best to get caustics. Now, caustics is the light that reflected light off water that you see on the underside of a bridge or a building. And so we did some analysis there to model what that would be like with different types of light and different types of sort of agitators to the water surface. So yeah, that was all the modeling. We also had to do all of our kind of more general engineering calculations to size our pipes, wires, and ducts, and all those sorts of things. But yeah, once that was all done and the building design was frozen, we would use all that modeling and analysis to design the building services. So this could be the more kind of exciting stuff that I enjoy the most. So like your heating, ventilation, cooling, lighting, hot and cold water design, but also a whole load of other stuff. So electrical design, access control, fire detection, data, comms, above ground drainage, and kind of knowledge of all these elements together is why kind of as a profession, we are probably known as knowing the most about how buildings work, which I'll get onto the importance of that a bit later. Cool. Are we really 20 minutes in? All right, I'm going to rocket through this. I'm going to give a real quick example of the nitty gritty. So just one element of the design of, again, another really, really nice project that I was able to work with on when I worked at Max Fordham. So this is St Ives in Cornwall. This is a graveyard, a big one actually. And this is an old art gallery, and this is a new one. The old Tate St Ives was designed and it finished in 1993 by architects called Evans and Shalev. And then there was a new brief to provide 500 square meters of gallery space, so an extension to the original Tate. So, and that's this building here, and the gallery space is kind of subterranean. It's built into the cliff, and it's just here. It was a competition. We were part of a competition team with Jamie Faubert Architects and Price and Myers Structural Engineers. So like I say, the core, that's the core design team. And then the brief was very, very heavily focused on the magical natural light of St Ives down in Cornwall. And there were other things like no light being allowed, no direct sunlight being allowed on the walls so that you could hang art and the art wouldn't degrade. Like I say, it's built in a cliff. There was a low energy brief, not quite as strong as probably what you would get these days. The design happened nearly 10 years ago now. And yeah, it's a very, very beautiful building. And again, the magical natural light. So will it let me go down? Come on. All right. I think I'm back. Not quite though. Sorry, my computer's catching up. Gives me a breather. All right, that's gone too far. What can you see, Ellie? Oh, right, hold on.
Oh, too far. I'm on the briefing process.
I am too, but I don't want to be. Oh, come on. I should have sent you the presentation and you could have done the clicking.
All right.
Have
you clicked back?
You still on the briefing process?
Yeah.
Huh?
Yeah, I am. What are you on?
I'm now on the brief.
Okay.
But it's
Oh, I'm on the brief. I'm on the brief.
Yeah, that's not. It keeps on going forward. This is mad. I mean, if anyone's got any questions this far, then if you can still hear me, then this might be a good time to go through them.
Pop in.
Oh. Yeah, I know. It's now going mad up. Oh, hold on.
It's going back. Maybe. Oh, there we are. There we are.
Yeah, that's the one I want. But now I've overdone that, haven't I?
I'm starting from the beginning.
Nah. All right, here we are, I think.
Yeah.
Right, fine. That's not going to ruin my flow at all, is it? So the magical license. So what does that mean? It's heavily in the briefing process for the building. It's often mentioned by locals in the area. It's mentioned by tourists and probably by most people who travel there. They come back talking about this natural magical quality of the light. And I suppose I felt it. I'm not that cold of an engineer that I would see something like that and just think of it in numerical terms. But at the same time, working on the project and being an engineer, I did want to put some sort of logic to it or tangible, I don't know, phenomena to it. So my thoughts are that it's because of the wide horizons that you get down there. It's got sea on the north, the east, and the west of it. There's plenty of weather as well. So as well as getting a lot, seeing a lot of the sky and seeing a lot of the sun, it's right down the southwest of Cornwall. So you get a lot of weather rolling off the Atlantic. So you get a lot of the sun sort of peeking out of behind the clouds and going into the clouds and that sort of stuff. And then around the area, there's lots of beaches and granite as well, which kind of reflects a lot of the light in a very impressive, mysterious way, I suppose. And this kind of gives you an a better impression of what I'm talking about is the kind of the power and the color temperature of daylight changing through the day and year. And like I say, people enjoy it. It's magical to some or science to others, I suppose. Okay, good. So the architect's brief was set, and a lot was hanging on this sentence actually. So while perfect for artist studios, the use of only north light in gallery spaces designed in the 20th century was a big mistake. It's too cold. But then no other gallery in the UK had incorporated south light within their main art hanging space. And so what that first sentence really means is shown on this, this graph here, that if you imagine standing looking north, you're never going to see the sun, or unless it's midsummer, and you might see it to your left because the sun will be setting in the northwest, or in the evening, or in the morning. If you look to your right, you might see it. But generally, in the UK, if you're looking north, you're seeing the sky and not the sun. And that's up here, that's blue sky. And then down here, you get these warmer color temperatures. So you get direct sunlight at noon is kind of like white. But then at either side of noon, you get into this warmer area. So sunset and sunrise is down here in the orangey reddy bit, which is 2000 Kelvin is the units that they use for color temperature. But okay, so I'm trying to set the scene here for how important it was to basically get this quantity of natural light within the space. But on top of that, there were all sorts of other things. So you needed to limit exposure to a certain amount of lux, and that's the amount of that's the light intensity. And then also to look at art well, you need good uniformity, so no bits where it's really bright and really dark, and then all the other kind of building performance stuff like low heat loss, low air infiltration, and aesthetics. This picture here is just an example of what would happen if you did leave an oil painting out in the sun. The bit on the right's been left out and the bit on the left has been protected, and you see that dulling of the art. This here is what we work to. Within a design team, that's the design stage through stages 0 to 4, and then down here is the construction. So we as a consultancy are heavily involved in design, and we normally get on board at around stage 1. Stage 0 is a client deciding what they want to build. Stage 1 is the kind of preparation of that brief, and then we have more involvement and engagement within the concept design, the developed design, and then the technical design. After technical design, we compile all of our design information, and that will go to a builder, and the builder will price how much that's going to cost to build, and then they'll build it if they're chosen. And we will have more of an overseeing role within the construction and handover period. I suppose that's just a bit of added context of where and when our work happens. So yeah, this is like a conceptual design. So we had that brief, and we spoke lots with the client, so the Tate Gallery as a client body, and also the architects, and came out with these sorts of sketches. And then we would take them to the architects and discuss the kind of merits and drawbacks of each one. And as we got a bit further, we got into some technical stuff. So this is us with cardboard and tape building a replica model, and that's a pavement outside the office and a sunny day, and we put someone's phone in our box, our technical box, and we took photos to see whether our conceptual design worked. Obviously we had done a bit more than this, but this was an important process because it was like something that we could see working and something that we could take to the architects and the client. And funnily enough, they didn't laugh at us. And this is the kind of outcome and the output that you'll see: a photo of the inside of a cardboard box. And this is the top. So you can see here that there is direct sunlight hitting the top of those rafters, but there's not any hitting the walls. So after this, we were kind of getting a bit more confident. This is a bit further on in the design process, sort of stuff that is maybe between conceptual and technical design. And this as a strategy didn't actually work, but I'm just showing you the level of information that we're getting towards. One more thing, so this was another kind of one of our roles, I suppose, is being able to communicate the results of our kind of really quite complicated analysis using our sort of simulation models and our computer models, but being able to communicate it in a way that people will understand it. So this was quite a powerful presentation. I thought it's got a bit of everything here. This isn't actually a photo. This is a render from our computer models, and these are the results from the computer models. This isn't actually the Tate. This is the Hayward Gallery in London, but just pretend it is. And the Hayward Gallery has these triangular roof lights, and the problem that we wanted to solve here was how much shading can we have within these triangular roof lights, or how much light can we let in but not get light on the walls again. So here we've got a kind of optimization process. So here, as you can see, we've taken the shades down from the top a certain amount, and okay, it's quite nice and bright in there, and there's definitely not any direct sunlight on the wall, but we can probably go a bit further. So we go a bit further, and it opens up, and as you can see, we're really close to getting sunlight on the wall, but we don't have it. And then we take that process a bit further, and we've gone a bit too far. So there's direct sunlight on the wall there. So we then need to just rein it back a little bit, and that there is the geometry that we would then give to the architects. I hope that happened at the right time, Ellie, or was there a lag? It did. All right, cool. Very good. All right. We'll get onto carbon soon, maybe. Yeah, this is just a slide to say that we that this is the results from our computer modeling. This was then taken from our report, and the measured light output on the walls was within 1 to 3% of our computer modeling. So that was, again, another like success out of the process, and good fun as well, because it was an opportunity for the people doing the modeling to actually go on site and make sure that their modeling technique is relevant or accurate to real life situations, which it was. This is an example of some construction information. It's not actually an engineering drawing, this is an architectural drawing, but everything in this architectural drawing is the parameters are set by us. So all of those dimensions, all of those angles and everything come out of our modeling process. Also, these things here are the ducts that are pushing the air into the space and also taking away the stale air from the space too. So that's another part of what we do, obviously. And then this is what it looked like inside. I mean, it was really, really impressive building. I mean, it still is. It's going to be there for years and years and years. It's very solidly built. And again, I mean, look, a proof of our modeling being quite close to real life. I mean, they're very, very similar there. This is another picture, and this is what they look like from the outside. Again, quite impactful kind of structural and architectural design that we led. We led the team, but also, yeah, getting it to look as nice as that is certainly something that an architect can do, and not me or most of the engineers that I know. Not quite as aesthetically cute as architects. And then just finally on this, good. Nice. This is a feedback from one of the architectural critics of The Guardian, so Ollie Wainwright, who said, environmental engineers Max Ford and modelled the precise lux levels allowed by international standards for the display of art, from which the architects generated their form, designing 6 light wells 4 meters deep, topped with honeycomb filled glass. So that was kind of the outcome of a, I don't know, 1.5-year design process. And of course we were working on other stuff at the same time, but yeah, that's a nice piece of work that that shows what kind of work you'd be doing as part of a team. A very sort of environmental design driven. So then what do I do? That's what you could be doing as a building services consultant or engineer. But what do? And what appeals to me? So there's 2 reasons. There's the decarbonisation aspect, but also the human aspect of engineering that I really enjoy. So so kind of success for us isn't a beam not failing or a component being lighter or cheaper. Success for us is an internal environment that is comfortable for its human occupants. So it's designing windows that are placed to let light in, provide views, or open wide enough to allow enough air in winter, but don't let in excessive heat out in winter and don't let too much in summer. So it could be designing ventilation systems that control humidity, CO2 concentrations, indoor air quality, drafts and temperatures to allow optimum conditions for kids learning in a classroom. And then it could also be the designing of heating or mechanical systems that reduce energy use. So that sort of comes back to success for us being an internal environment that's comfortable for its human occupants, but then there is the external environment as well. If we do a really, really good job, then we can significantly reduce carbon emissions from our buildings. So that gives us a chance to have a comfortable external environment as well as internal. I don't think I've got anything else to say on this slide, but I have blown up that concentration of CO2 in the atmosphere, which is a scary graph. It's not a very nice graph at all. It shows from the 60s to now the concentration of CO2 in our atmosphere increasing by about 1/3. We're currently at about 420 parts per million, and that's the highest that's ever been recorded during the whole evolution of meetings to talk about climate change and carbon emissions. And as you can see, they're not really having much of a dent on that upward trajectory. So yeah, to go with the bonus COP slide, there's the bonus climate anxiety slide as well. One that I, fall prey to often. So yeah, there's all these horrible things that are happening as well. Insects kind of collapsing, and extreme weather in warm places, and humans driving species to extinction, which yeah, is horrible. All that other stuff. And the center of that is that carbon dioxide emissions are set for the second biggest increase in history for 2021. And 2022 is probably going to be slightly similar. So although I've given you a big old talk about the fun part of building service engineering, my day-to-day these days is more focused on emissions. My private life is too, but this is quite kind of the bigger focus for me now, is reducing the 23% of the UK's emissions. So sorry, that wasn't very clear. Currently, buildings, if you include the electricity used within buildings, take up 23% of the UK's carbon emissions. And I mean, that's kind of crazy, because we've got the technologies and we've got prototype buildings already built and already refurbished as well of our existing housing stock that is very, very close to zero carbon. And some of them are, I suppose, mini power stations, as in they generate more electricity than they use. So yeah, this is a graph from the CCC, so the Committee on Climate Change. They have really, really good reports and information. They're an impartial governmental advisory body. And they basically comment on how we're doing in terms of our road to net zero carbon in 2050 and those interim targets that we also have. This is a graph with a yellow line in, so it should be made illegal, because graphs with yellow lines are not good. But the yellow line is kind of important. It shows the decarbonisation of the electricity supply, while also showing that we're not really decarbonising much in other sectors. The only other sector we're really decarbonising in is manufacturing, construction, and generally that's kind of because we don't really do as much manufacturing and construction of the goods that we use and we consume now. That's kind of been offset by getting other countries to do it. But it's so what this means is there are headlines that say that we have reduced our carbon emissions by 40% since 1990 emission rates, but really that's just been due to the phase out of coal and it being replaced by wind and solar, and also us exporting the emissions for the manufacture of quite a lot of our kind of consumable goods going to Asia generally. It's also worth looking at this graph to see this line here in kind of orange, I suppose you could call it, and you can see that the emissions from buildings has kind of just stagnated in the last 10 years. It's not gone up and it's not gone down. So what can we do? I was quite close to changing career after my third year of traveling. I had read lots of stuff, a bit like that slide before with the fires, and about sort of the implications of the increase in carbon dioxide in our atmosphere, and how best I can sort of help our path to decarbonisation. But I couldn't really find anything that would have a bigger difference than buildings, really. Buildings have a very large portion of the pie, that 23% that, of emissions that are attributed to buildings. The only bigger sector is transport. And I don't really know anything about transport. But the solutions are already here for us. And the final two slides, I will explain that. But here kind of is the issue currently. We've got our average existing home. So if we just talk about the domestic emissions now, is up here at about around 17,000 kilowatt hours per year. That kilowatt hour figure isn't important. It's the reduction that we're focusing on now. So a new house, you can almost cut that in half, because new houses have better windows, better walls, more insulation in their lofts and on their floors and everything. And then you can cut your emissions even more if you don't have a gas boiler, but you do have an air source heat pump. I'll talk about air source heat pumps in a bit. And then you can go down even more if you go to a passive house. And again, I'll talk about Passivhaus in just a bit. This reduction here doesn't look like much, but it's the main driver for Passivhaus, as well as having a very comfortable building. It's to reduce the space heating. So if you look at what you've done to the blue bit, the space heating, by having a passive house, you've thirded a new build with an air source heat pump. So it's an enormous factor of reduction when you're comparing it to any of these, an average home, a new build with a gas boiler, or a new build with an air source heat pump. And so that kind of brings me nicely onto Passivhaus. These 4 buildings are Passivhauses. They're a really nice selection, actually. The one on your top left is a building that was built in the 1890s, so a semi-detached arts and crafts property, and it was retrofitted to Passivhaus standards by Ecospheric, the consultancy that I worked with at the beginning of my career. The next one, just down to the bottom right, this is Max Fordham's actual house. So again, the consultancy that I worked for second, the founder of that consultancy has built his own passive house. So that's up in Camden, in North London. And then the bottom left, this is a passive house school. So it's a school in Wolverhampton, and that's an E3 project. It's the first passive house primary school in, the second generation of passive house primary schools in the UK. And then the fourth one on the top right is a whole development, so a whole social housing development that won the Sterling Prize, and that's called Goldsmith Street in Norwich. And so that's a very cost-effective passive house development. So you've got a bit of everything here. You've got a nice new build at the bottom right. You've got top left, turning a real old energy inefficient property to a very efficient property. You've got a different use of building, so a school, and then also a cost-effective development as well. So it does cover a lot of the basis. And like I showed on the graphs earlier, that's how you get from an energy up here being this big to being down here. And so just quickly, these are the 5, what are they? The 5 concepts of passive house. And it's really simple. You have thermal insulation. So you make sure that your building is really, really well insulated. That means that you lose very, very little heat in the winter. So it means that your heat bills are very, very low, or your energy demand is very, very low. But it also can help in summer as well. When it's very, very hot outside, it means that you're kind of insulated from those real peaks in the middle of the afternoon, which with our warming climate are going to become more and more of a problem. The second one is Passivhaus windows. Generally, this isn't necessarily for energy, it's for comfort, is to have triple glazed windows. So you don't have any cold patches on your walls. If you have a poorly performing Clifton house, or a lot of the houses in Bristol are, and they maybe have bad double glazing or even single glazing, if you're sitting close to that single glaze, you know about it. You will be wearing a hoodie. You won't want your neck to be exposed to it if you've got your back to it. It's uncomfortable. So passive houses have triple glazing. Then this thermal bridge reduction, I'm not going to spend a lot of time talking about thermal bridge, but that
Dave,
basically ensuring that there's a continuity of that thermal insulation around the whole building. So that's what thermal bridges are. So again, it's a more rigorous design where you're taking into account all of these things. And air tightness. So air tightness and adequate ventilation strategy are kind of the same thing. It's how you get your fresh air in, and making sure that you don't have drafts, and making sure that you recover that that heat energy from the outgoing air. Can you hear me all right, Ellie, or is there background now?
No, really can. Would we be able to do some questions soon? I'm just conscious.
Yeah, we're very close. I've got two more.
Of course, thank you.
So that's Passivhaus, and now I've skipped the wrong way. And then sort of the last one, if it's going to come. So this is an air source heat pump. And so these are spoken about a lot, and it's what we use, or what we're keen on using instead of gas boilers. Gas boilers will always emit carbon dioxide. You're burning gas to get heat. A heat pump doesn't really work like that. It works like a fridge in reverse. So it's the electrification of heat. And that's really, really important, because let me just go 2 more slides and then we can do some questions. Because with this air source heat pump, you end up being able to link everything together. So if you've electrified everything, so you don't have gas, then you've got the potential to have your PV array that goes into a battery that might go into your car, that might go into heating your home. So you have this link around your house where you can then reduce not only your emissions from heating your house and having showers, you can reduce your transport emissions, because you could charge your electric car, or you could charge your electric bike, or even better, well, not even better, but part of that is that you could charge your battery during the day when it's either windy or sunny, or both. And then in the evening, when it's not sunny, you can then either use that stored electricity from the battery yourself, or you could push it to the grid. So it means that your neighbor is using low carbon electricity instead of using higher carbon electricity. I've still got some gas for some questions, but yeah, sorry that was rambly. That's kind of how my presentations roll.
No, not at all. Thank you so much, Dave. Are we okay to go with some questions?
Yeah, do it.
Fab. Does anybody have any questions? Do you want to unmute or put your hand up?
I have a question. I just want to ask about passive houses. How much more expensive would a passive house be compared to a normal house, with all the additional insulation on the windows and air tightening features?
Yeah. That's a real common question, and because it's such a common question, there's some really good documents that answer it. So either on like the Passivhaus Trust website or the Institute for Passivhaus, they have like nice kind of 4-page explainers. But the differences are in, as you say, there's more insulation, so that costs a bit more. There's also, you need to get a far lower air leakage rate with a passive house. So that costs a bit more because you need some tapes and you need some membranes and you need to do it properly. There's also the additional cost of windows. For example, passive house certified triple glazed windows might be 20% more in cost than an equivalent double glazed unit. So it's really hard to do a like for like question, because what you get from doing a passive house is so much more design rigor that you can really easily start to identify ways of cutting costs as well. For example, in a passive house, you probably, unless you had a stunning northerly view, you'd have smaller windows in the north than you would otherwise. So you only really know to do that because you're spending a bit more time looking at the energy flows of the building in the passive house spreadsheet, which is called PHPP. What you might also do is end up designing, this is unpopular for people who aren't super carbon engaged, but you might end up designing a more space effective house. So you might end up still having a house, but it might be slightly smaller than it would be otherwise, because a smaller house will lose less heat, so it will be more energy efficient. So I don't know. Like I showed in the photos, there's plenty of examples both in Norwich and Exeter, another leading council, where they're developing passive houses for very, very similar cost to traditional buildings. But the reason why they're able to do that is because they've gone through the process quite a few times. So they know how the best way to build them and design them is, and they have quite good cost certainty over that. But yeah, to an average kind of like super engaged person who wanted to build them themselves, cost is unlikely to be the main driver for them, I'd say. I hope that answers.
Yeah.
Happy to have a follow-up.
Yeah, no, that's good. Thanks.
Lovely. Does anybody else have any other questions? I think.
Go on, Ellie, you must have a question.
Oh, I have so many questions. Oh, could you explain what an MVHR system is, please? Just like
Yeah.
in a nutshell.
Yeah, feel free to. I realize I've done my hour. I will not be offended if people start dropping off. It is Monday, so you can have too much learning for a Monday. But yeah, let me just go back to this slide if that will help, because moving through slides has been such a smooth process so far. Come on.
Oh no.
It's getting there. Okay. Well, while that sorts itself out, every house has a kitchen and at least one bathroom. It's a legal requirement to extract the air from a kitchen and a bathroom because it's stale and it's got high humidity, and that is unhealthy for both the occupants of a building and also the building fabric of the building. So what makes up the building. So that air needs to be taken from the room that it's in, and it needs to be pushed outside. Traditionally, that might just be an extract fan, and then the air comes from the front door or the windows or something like that. But what an MVHR does is it recovers the heat from that outgoing air, and it passes the heat to the incoming air. and then you supply that incoming air to a bedroom or a living room. And that means you get a constant supply of filtered air going into the rooms where you want it. So your bedroom while you're sleeping, or your living room while you're watching a film. And it's really, really useful in winter because it means that you get really good air quality without opening the windows. And it also means that you get disturbed a bit less as well because you don't let in as many sounds from outside. But yeah, I can't believe this slide hasn't come up yet.
No, honestly, don't worry. Thank you so much, Dave.